continue. Okay. So on to the real stuff for class today. So first, announcements. We talked about this Monday, a handful of upcoming things. One thing, correction from Monday that I didn't make beforehand is the due date of your finite hypothesis classes homework. I had originally stated that that was going to be in the middle of fall break, but I'm not going to look at it in the middle of fall break, and my hope is that you all won't look at it either, so that's extended until Tuesday. We'll still have the quiz on the definitions from chapter 2 on Wednesday, the first day back from fall break, our next class period. Any questions about administrative stuff, upcoming assignments? Okay. I have a short little announcement here thing that we'll get to in a couple of minutes in the middle of going over the notes. Otherwise, the only announcement new for today is enjoying fall break. So last time, let's review where we left off. We've been going over this chapter 2 here, training versus testing. Again, the point of chapter 2 here is to develop these generalization bounds based on the VC dimension. And we spent a lot of time talking about what it means to be the VC dimension of something. How is it defined? There's a lot of related terms here, like the growth function and dichotomies and shattering and breakpoints, and all of these terms are providing somehow basically the same information. But usually the way that we describe it in the most succinct way possible is with the VC dimension. All the other terms can provide the same information, but the VC dimension is the most important or the most commonly discussed way of measuring the size of a complexity class. And so again, the VC dimension here denoted by this DVC of H, or simply DVC. So there's one of those terms that's overloaded, that sometimes it has this function notation, sometimes not. We only use the function notation if we are talking about multiple hypothesis classes at once. Otherwise, we just say DVC by itself. And this is the largest value of n for which our growth function is exponential. One of the things that we saw last time is that the growth function is either going to be exponential like this, or it is going to be polynomial, and it cannot be anything in between. And if it is exponential, it in particular has to be exactly equal to 2 to the n. If it's not equal to 2 to the n, then it goes down to a polynomial. The other part of this is that if our growth function is always exponential, another way of saying that is if there is no breakpoint for our hypothesis class, because a breakpoint is a value of n for which our growth function is not exponential, but polynomial. So if there is no breakpoint, or if our growth function is always exponential, then we say the VC dimension is infinite. And then we talked about the generalization bound based on VC dimension, and this is sort of the most important thing from chapter 2. This is if there's one thing that you take away from chapter 2, hopefully there's more, but if there's only one thing you can take away, this is the thing to take away. The rest of chapter 2 is just building up to this theorem right here about the VC generalization bound, and in particular giving us enough background to understand exactly what the VC dimension is down here. One of the things we talked about with this generalization bound here, and I'm going to write some stuff again, but there's all stuff that I've written last time, so don't feel a need to copy verbatim everything I say. That should just be trying to absorb the vibes of how I'm saying it here, the way that I think about things at this point. One of the important things here, or I guess two important things here, are one, that the bounds here, all of these constants are very loose. These constants are very loose, and like very with a lot of underscores in here. Very loose. And in practice, data mining people do not care about these sorts of constants. The only thing that we care about is the relation between the VC dimension here and the number of data points that we need. So that's one thing. The other thing is that why do we care about these bounds if these constants are so loose? Why do we care? The first reason that we've seen, that we've talked about, why do we care? Reason number one is just that it proves that learning is possible at all. That if our VC dimension, if our DVC is less than infinity, then learning is possible. And what I mean by learning is possible is that as we get enough data, as we get enough data, so the in value going to infinity, that will imply that our generalization error goes to 0. That implies that our in error goes to E out. And that's the absolute minimum thing that we could possibly want from a learning algorithm, is that when we have unlimited data, and ignoring computational problems that might arise from unlimited data. But if we had unlimited data, then we should actually be able to come up with the true distribution of things. Our E in here is going to E out. So that's the first thing about why we care right here. And that's where we left off last time. What we're going to do today, we're going to finish these notes and go on to the next notes packet, which is going to help us review a lot of the terms that we've seen so far from this chapter 2. And then maybe we'll start on chapter 3 stuff a little bit, depending on how fast we go. So here, this why do we care, we're going to see a more detailed explanation of why we care here in 2 problems at the very last page. But before we do that, we're going to do this problem right here, problem 3, of what is the VC dimension of the perceptron hypothesis class. In general, from this point forward, whenever we see a new hypothesis class, this is always going to be the first question we ask ourselves about that class, is what is the VC dimension of that class? Because that will tell us how well we're going to generalize and if learning is even possible on that class. So we've actually sort of already done this in secret in the special case of d equals 2. In the special case of d equals 2, we've already done this. We showed that m sub h in this case of, and this was in problem up here. This is problem 1, example 2.1, page 4.3, calculating the MH3 and MH4, the growth bound, the growth function on 3 and the growth function on 4. And again, this growth function is very closely related to the VC dimension. So let's see, that's not growth function of 2, that's the growth function of 3. We saw that this was equal to 2 to the cubed, which is equal to 8. So it is exponential in this case. And we also saw that MH of 4 was equal to 14, which is not equal to 2 to the 4th, so not exponential. And the VC dimension, again, is the largest value of n for which the growth function is exponential. So all of this together implies that in this case, the dVC is going to be equal to 3. So when our dimension is equal to 2, our VC dimension is equal to 3. And that's something that we have already shown. Now what we're going to talk about is the more general case here for arbitrary dimensions. In general, when we talk about hypothesis classes, from now on out, we're not going to be interested in the VC dimension in a specific value of d. We want a generic function of the VC dimension, a generic expression that tells us no matter what the dimension is of our input data, what's the resulting VC dimension. And so now down here, a generic analysis of D. The general procedure for proving a VC dimension bound is you always, this is going to be a procedure that's familiar for people who've done like analysis sort of courses before, but we're going to provide, do a 2-step thing. We'll show that the dVC is greater than or equal to some value, we'll say k, and the dVC is less than or equal to some value k, and both of those two things combined together will prove that the DVC is equal to K. This is the general procedure for showing VC dimension of a hypothesis class. And when we show that the first part over here, this part 1 right here, DVC greater than or equal to K. Part 1, what we need to show is that, well, in this particular case, what we will argue is that the DVC is greater than or equal to D plus 1. And in order to do that, all we have to do is find any particular data set, find any data set of size n equals D plus 1 that shatters, or that H can shatter, that the perceptron can shatter. Again, shattering, we had 3 equivalent definitions for. One of those definitions is that we can assign all possible class labels to any of the data points. Another definition is that the size of the dichotomies is exponential. So this here is equivalent to saying that our growth function is exponential. This thing right here, this verb shattering, that the perceptron shatters, that's equivalent to saying that mh of n equals 2 to the n. Again, lots of different definitions that we introduced last time in class that all people do in fact use them all when they're talking about things. They're convenient to use, different ones convenient to use in different situations, and so you do have to be comfortable with all of them. The let's see, the actual technical details of this proof of finding this data set of size n plus 1 that the perceptron shatters is rather technical, and so we're not going to go through the mechanical steps of doing this. It's a bunch of tedious linear algebra, and my sense from doing that in the past with students is that nobody's convinced by anything by going through that tedious linear algebra. If you are interested in going through that linear algebra, it is available at this link right here. And that link will take you to the, where did it go? This page about the textbook, and so the textbook author right here, this guy from Caltech, he walks through the tedious algebra there if you would like to do that, or look through the lecture slides right here to walk through the algebra. So if you are convinced by algebra, then you can do that. But the intuition here, this agrees with our D equal 2 example up above, that here with, if we had D equals 2, then we could come up with a set of size D plus 1, size 3 that we were able to shatter. And the intuition there is, I think, the important part. So DVC greater than or equal to D plus 1. And then similarly, do it, and we'll go red. The other bound, part 2 right here, in order to show that the DVC is less than or equal to D plus 1, it's not enough to show one data set that we cannot shatter. We must show that all, all data sets of size, in this case D plus 2, whatever the bound that we're trying to show, plus 1, all data sets of size D plus 2 cannot be shattered. all data sets of size d+2 cannot be shattered. Again, showing this is a technical linear algebra thing that is, I think, not important for our class, so we're not going to go into those details. But the important thing is that on the first direction over here, showing that the VC dimension is greater than or equal to something, all you have to do is find a single data set that can shatter that. But to show that the VC dimension is less than or equal to something, you have to be able to show that all data sets of that size cannot be shattered. So this is a for all statement right here. For all, this is a like just there exists statement, any statement up here. On the next note packet, we'll do some more examples of doing this in a little bit more detail. But this is going to be the important thing. Anytime you're asked to justify why the VC dimension is what it is, this procedure of showing that it's greater than or equal to something, showing that it's less than or equal to something, and to do the greater than or equal to, it's a find any that shatters, and for the less than or equal to, it's show that nothing can shatter it. I believe all the numbers here are correct, but let's walk through it again. So, I was just wondering on the, whether you're yeah, so I believe those are correct. I'm going to walk through it just to double check this. So my claim here is that the VC dimension, so the overall claim, what I've tried to prove here is that the VC dimension dVC is exactly equal to d+1, and this is a true statement. And in order to show the less than or equal to, that the dVC is less than or equal to d+1, I have to find a breakpoint of our hypothesis class that is bigger than this. And so that is this thing right here. If we call this thing right here, I'll call it k, it's a good constant. This thing right here equals k+1. Finding something that is larger, exactly one larger than this thing over here, shows that this thing is true. So yes, those numbers are correct. Good question. So this is an exact formula on our VC dimension for the perceptron hypothesis class. We will see that for most classes that we're interested in, we actually cannot have exact formulas, or we do not know what the exact formulas are. It is an open problem to compute those exact formulas. And so in general, we just think about the theta bounds of these VC dimensions. And so people will talk about the perceptron as having a d+1 VC dimension, or people will talk about the perceptron as having a d dimension, sort of not even saying theta of d, just saying that it has VC dimension of d. And we don't really care about the difference. Again, the only way the difference between d+1 and theta d could come into play is up here if we cared about the constants, but we don't care about these constants because they are so loose in practice. And so we just care about the sort of asymptotic notation here of what the VC dimension is going to be. We care about the asymptotic bounds. VC dimension of perceptron being theta d, definitely something that if you walk into any interview for anything remotely related to machine learning, this will be like expected knowledge. And if it's not something that you can instantly pull out of your hat, guaranteed no job offer. This is like the super important thing to take away. Everybody knows this. Okay. So why is this important? That we talked, so we have one justification of why it's important so far, that we know that learning is in fact possible because our VC dimension now is finite. And so we know if we have an infinite amount of data, then we are going to eventually converge to the true error. with enough data, our in-sample error will converge to the out-of-sample error. But there is a better reason for why this is important. And this is a reason, so the textbook discusses this stuff up here. The textbook does not discuss this stuff down here, this sort of application not in the textbook. And the sort of reasoning that's going to happen here in problem 4 is the sort of thing that, again, there is no textbook that discusses this. So not just not in this textbook, not in any textbook. But there's a sort of assumption by textbook authors and people who work in the field that if you understand the stuff up here, then the stuff down here is going to be obvious. Not in any textbook, because it is, in the opinion of those authors, too obvious to bother writing down. But it's also the most important thing that practitioners do. This problem here comes from a capstone project that I was working on with students. And this is the type of reasoning that you have to be able to do in your head while talking to clients in a capstone sort of project, or if you are a machine learning engineer at a company. So this type of application-y problem, again, super important to be able to do. Okay, so what is the problem? So you're a bank using the perceptron to learn a formula for whether or not to issue a loan. You have successfully learned a model on some data set where each x sub I has d features. So I'll just write some things down here, summarizing what the problem's saying, that the number of data points still equal to n. So that's just the notation from the book. Just rewriting this same down. There's nothing new here. Same number of dimensions or features equal to d. And but the actual fundamental problem here is that our training error is too high. Our training error of the model too high. So En too high. And we have to ask ourselves, what are the possible things that we can do to solve this problem? Again, the training error is something that we do measure directly. We can measure directly. There's an explicit formula for it based on our input data set here. So we know exactly what our training error is. And so here, and again, this is an exact situation that capstone students faced, where management, their clients, had some allocation of money to create a new data set, improve the existing data set that we had. And we have two choices here. So two choices. The first is that we can either add new features to the existing data set. So choice 1 is to make D larger. Make D larger. And the second choice here is to add more data points that all have the same features. Add more data is make N larger. So just labeling, that's the part 1 right here. This right here is the part 2. And so according to all the theory stuff that we have talked about, which one of these two options is going to be the best? Well, the VC dimension stuff, the only way that N plays a role, the only way that N factors into any of our equations that we've seen, that N plays a role, is that the generalization error En minus E out is bounded by the O of square root dVC divided by N, and again, ignoring some other terms that are not important for our current discussion right here. And so this is not related to our problem in any way. Our input error is too high. It's not that our generalization error is bad, it's that our input error is bad. Our in-sample error right here is bad. So this can't possibly help. These two things taken together increasing in up cannot help. It does not have any effect on our in-sample error. And in fact, that I'll say that so that the in value going up results in either the in-sample error staying constant, or actually it's possible that the in-sample error will go up, but it will never go down. So this is the only possibility that makes sense. Only possibility that makes sense. And again, in sort of like an interview situation, nobody's going to ask you to calculate the VC dimension of something, but they are going to ask you some sort of real world situation like this, and being able to argue through the way that the VC dimension impacts things, the way that our in and our d values impact things is a very important skill. One of the things that you will see in your finite hypothesis classes homework is that, in fact, as you make the number of features here d larger, you will, in fact, see the in-sample error go down. And that's a thing observed from practice. We haven't explicitly discussed a theory that says that, but d increasing will imply that En either goes down or possibly stays the same, but never goes up. So yeah, super important line of reasoning here. Any questions about that? Yeah, good.
Can you explain why increasing it might not decrease the end?
Might not decrease?
Or like lower the in-sample error. Like if you look at the relationship between two, like as you increase n, that fraction should get smaller.
So yeah, so the in-sample error here, the in-sample error defined as 1 over n sum I equals 1 to n of here the h of x sub I not being equal to the y sub I, like that. And the question is, like, if we have an in the denominator over here, if we have an in right here, why does increasing in not make the in-sample error go down? And the answer is because of this summation over here, that even though we make this in go down, this in, it goes up, and so we're adding more plus ones to it.
So I was asking more about the inequality above that.
This. So this in here going down, in going up here makes the generalization error go down, makes the difference between E in to E out go down, but does not make the in-sample error go down.
So does that imply that out?
Does that imply that E out increases? The answer is no. Let's see. So one graph that we haven't talked about yet, probably 2 sets of notes will graph something that looks like this, but we can go ahead and graph it now. That if we have, say, in on the x-axis down here and different error measures on the y-axis like this, the E out looks something like this, and the E in looks something like this. And so the generalization error bound of this difference gets smaller. As in increases implies this gap shrinks. So I might have, I think maybe what you actually asked was, does E out get smaller? And if that was the thing that you asked and I said no to that, then I was wrong. The E out does get smaller. But in particular, it's that both of them are getting closer to this, they converge together to the same thing. Did that answer your question there, Kevin? Okay, I'm okay.
Is there a name for this dash
Question is there a name for this dash point? Yes, there is. This name right here is called the bias or the approximation error. The textbook starts talking a little bit about this in section 2.3. They also talk about it more later on in chapter 3. I think it makes sense to talk about it all together. So we'll talk about it all together in the chat when we talk about it in chapter 3.
When we go up to the property,
This direction?
so we're saying that, yeah,
About the problem?
oh, yeah, sorry. Okay. Why, can you explain why DVC increasing flows again?
Why does DVC increasing lower EN? So this goes back to, let's see, where can I find a space to write? I'll scroll down here. That if we have H1 is a subset of H2, this implies that En of G2 less than or equal to En of G1, and the increasing the dimension going back to the notation in the problem, this is like our dimension equals D, dimension equals D is a subset of the dimension equals 2D functions. And so the 2D functions, we might not end up improving our in-sample error, but we're guaranteed to not make it worse. We can only make it better by increasing the D here because of this subset relation.
So we're assuming that increasing the dimension. So that's
for the it's not guaranteed that increasing, there are hypothesis classes that would be like counterexamples to that, where increasing the dimension of the data does not increase the number of elements in the hypothesis class. But for the perceptron hypothesis class, it is the case that increasing the dimension increases the number of hypotheses, because H perceptron, again, defined to be, skip all this stuff, the important things after the colon, where the W contained in R to the D. And as D gets bigger, this space over here that we're sort of looping over gets bigger. And so the number of stuff over here gets bigger. I'm going to have to, if there are more questions about this, which is a reasonable thing to have more questions about, I'll have to take them later. I need to keep going a little bit. So, so this is the first part of the problem about what choice to make if your in-sample error is too high. Part 2 down here, so saying, okay, we decided to augment the data set so that it now has 2D features instead of only D features. And now the problem is the generalization error too high. So E in minus E out, too high. And this makes sense. Why does this make sense? Because D increasing implies that the DVC increases. And then so by the VC dimension bound, generalization bound, implies that E in minus E out, which is bounded by O of square root DVC at the top divided by in at the bottom, implies that that thing's going to increase because the numerator over here increased. Because the relationship over here is linear between DVC and in, then that allows us to answer this last question in the problem where it says, according to VC theory, how many more data points will you need in order to achieve the same generalization error that you had before? Well, if DVC increased by a factor of 2, that implies that in needs to increase by a factor of 2 in order for this ratio to stay the same. So for O of root DVC over in to be a constant. So the actual answer here, increase by twice. And this is like the purpose of the VC dimension. This sort of analysis right here, like we don't need to know about the looseness or tightness of the bound in order to be able to do this sort of analysis that tells us like how much more data do we need in order for the same generalization error to appear, or whether we should increase the amount of data or the number of dimensions in a particular problem case. So this is all like a sort of high-level intuitive thing that that data miners actually use in practice when we're applying these sorts of bounds up here. Statistician sort of people, where'd it go? Statistician sort of people, they care about the constants in these things and they plug things in, calculate p-values. Data mining people, we don't care about that stuff. We care about like the intuitive direction about what does that tell us that we need to do to make our problem behave better in a certain situation. Okay. Yeah, again, if there's more questions on this, happy to take them later. But I want us to make sure that we spend some time on this chapter 2 set of notes, because it's the second set of chapter 2 notes here, because they have a lot of problems here, which will help clarify a lot of the technical detail aspect of the last set of notes. Set of notes divided into 2 basic problems. Problem 1 up here, calculating the VC dimension for different things. And then problem 2 down here, a bunch of these sort of trivial problems, provide a counterexample about the relationship between all of our different definition terms. For problem 1, part 1 here, we'll go ahead and work through this in class. Most of these I won't do in class, and you'll have to do them on yourself, including understanding what exactly is this like hypothesis class, what is that trying to do. But so the first way to tackle any of these problems is to understand like what is the picture meaning behind these hypothesis classes. And in this case, it is a one-dimensional thing. So our X input here is not a vector. It's not in the bold font. It is a scalar in the non-bold italic font. And so our visualization is just going to sit on a single straight line like this. And I'll go ahead and label an origin in here somewhere. And then if we have some data point like this, so this is an actual data point in our data set, then what our function inside of here is doing, what our hypothesis is doing, is we pick some particular a value, and it's called the set of positive rays in one dimension because this hypothesis class is commonly visualized as a ray or an arrow leaving from one point and pointing off to infinity. And they're positive rays because they only exist on the positive side. Here, if our a value, make this a little bit concrete, say that a value is equal to 1 and this x value is equal to 2, then 2 minus 1 is positive, so our sign value here is going to be positive. And more generally, anything to the right of this a value is going to be positive. Anything to the left of this a value is negative. In order to talk about, again, shattering a data set, we have to, for any one of these points in the data set, we have to provide all possible labelings at that point. And in this case, we can shatter this data set because we can move this a to, say, over here, try this value where a equals 3. And now in this ray, we'll have positive on the right of the a value, negative on the left of the a value, and now we've assigned this x right here as either positive or negative. So this tells us that the VC dimension dVC must be greater than or equal to 1, because we have found a data set of size 1 that we can shatter. Question?
Why is it only positive rays when a belongs to a set of real numbers? So can't a be negative?
So the question is here, why is it only positive rays? Because a belongs to the set of real numbers, and a could in fact be negative. If a is negative, so let's do a green here, like here, a equals -1. We have positives on the right-hand side, negatives on the left-hand side, and this would still be called a positive ray because the positive stuff here is shooting off to the right. The difference between problem 1 up here, part 1, and part 2 down here is, again, the addition of a sigma. So there's a very common pattern when designing hypothesis classes is in order to be able to flip your sign in either way, you add one of these sigma variables, which is +1 or -1. And this sigma lets you flip the direction of that classification. So this is in some sense just a terminology thing about why is this called positive. It's not the fact that A can be positive, it's the fact that the positive only happens on the right-hand side of the threshold here. Down here where the positive can happen on the right-hand side or the left-hand side, we call these the positive and negative rays in dimension 1. So again, anytime where you're calculating the VC dimension of something, then you have to provide an upper bound and a lower bound. So here we're saying that we're providing the lower bound, that the VC dimension is at least 1. And we can say also that the VC dimension is less than 2 by providing a data set that is of size 2, or arguing that rather all data sets of size 2 cannot be shattered. And doing that formally and technically, again, not super insightful. So being able to argue that, like the intuition behind why that's the case is what you need to be able to do for these problems. But all data points, all data sets of size 2 are going to be somehow representable like this, where you have 2 points in the plane, or not 2 points in the plane, 2 points on the line. And there's sort of like 3 meaningful ways that we can draw rays here. One where the A value is right here, one where the A value is here, and one where the A value is here. And everything else, all the other possible versions of A, somehow are going to be like the same as these 3 A values. And so here again, this A value, positives on this side, negatives on this side, positives on this side, negatives on this side, positives on this side, negatives on this side. And actually, this is enough right now to already argue that we cannot shatter this data set, because our number of hypotheses is, rather our number of dichotomies, I'll call this for clarity x1 and x2, x1 comma x2 is going to be exactly equal to 3, which is not equal to an exponential. And so that implies not shattering. Not shattering, which implies that the VC dimension dVC is less than 2, or equivalently less than or equal to 1, because it must be an integer. That is enough of an argument right there, but we can further say that like what is the actual arrangement, what is the actual dichotomy that we cannot achieve with this situation, and that is if we have x1 being labeled as a positive, x1 being positive, and x2 being negative, then there is no way for us, no value of A can achieve this particular labeling. No value of A can achieve this labeling. And so that is why that is the missing one of these dichotomies right here that we are not able to achieve. So again, this is not a formal proof. This is a intuitive argumentation about why the VC dimension is 1. The part up here is actually pretty formal. The part down here, there's some gaps to fill in here. But again, one of the purposes of this class is to get you sort of thinking and talking at the level the way mathematicians actually think and talk to each other. And nobody would ever bother actually formalizing this argument. This is enough to convince everybody. If I would bet even money that this like has never been formalized in the history of the universe right here. And so I would certainly not ask you to do that. So here the VC dimension is 1. We know that because of this, this bound that we've provided, greater than or equal to 1, less than or equal to 1. Down here, what's going to happen, I won't work through all the details, but what's going to happen is that we will now be able to shatter this particular data set, but we will not shatter any n equals 3 data set. And that'll imply that the DVC is strictly less than 3. And so the DVC for this problem is going to be equal to 2. Again, there's more gaps to fill in there that you'd have to explain to me, say in the midterm. But since we already started talking about this, I'm just telling you the answer right here. At least the other ones of these VC dimension problems I'm not going to do in class today. Maybe we'll do it a different day. But I want to jump down to problem 2 and talk about some of these problem 2 problems. Let's see, which ones do I want to talk about? So let's start talking about this first one here, where this is very similar to the, well, maybe not exactly the same as our quiz problem, but related because it's talking about f, the true labeling function here. And so let f be the true labeling function, then for all data distributions, e out of f is equal to 0. Again, these are like prove or provide a counter example problems. And this is going to be a false statement. And the reason for that is that any data set, any problem that has noise, sort of the definition of noise, any problem with noise will have our E out of F strictly greater than 0. And that was one of the sort of equivalent definitions of noise. Yeah, so I'm going to go through these a little bit quickly, not stopping for questions here because we don't have too much time left, and I want to make sure we do a handful of these problems. If you do have questions about any of these, happy to chat about that after class. Okay, number 2 here, let's do that one. So this is saying H here being the perceptron hypothesis class, G the result of the PLA, and then F be the true labeling function, E out of G greater than or equal to E out of F. This is true by the same arguments from our quiz. Oops, my thing is out of alignment. True here. That again, the F being defined to be the arg minimum of H in all hypothesis classes, union of all of the hypothesis classes of E out of H, H star being the union of all hypothesis classes. And so the result immediately follows from that. The quiz specifically about finite hypothesis classes, but that is true even when we're talking about infinite hypothesis classes. Let's jump over next to problem number 7. This is the first really interesting one of these problems. And that's that the VC dimension of every hypothesis class is finite. So this is not something that we've directly talked about yet. But we have talked about all the things that you need, all the ingredients to be able to solve this problem. The answer here turns out, in fact, to be true, and we will solve this by showing what the actual VC dimension is. So recall that our VC dimension is the largest n for which our growth function m sub h equals 2 to the n. And because if it's not exponential, then we're at a breakpoint, and then we're polynomial. And also recall that our m sub h, the actual definition of this, and I'll explicitly say mh of n here, this is the maximum over all data sets, over all data sets of the size of the dichotomies, h of x1, comma, x2, comma, up to x sub n. And so if we can bound the size of the dichotomies by some finite value, then that will also bound our VC dimension by a finite value, meaning that the VC dimension itself will be finite. It turns out that we can, in fact, bound that. One of the things that we talked about last time is that the size of a set of dichotomies, x1, x2, up to x sub n. The size of this, there are several upper bounds on this, but one of the upper bounds on this is the actual size of the hypothesis class. And in this case, because we have a finite hypothesis class, this size right here is equal to m. So m is in fact a bound on the size of our dichotomies, the total number of dichotomies that we're going to have. And since every one of those dichotomies, no matter the data set, is bounded by m, we have that this expression up here, the definition of our m sub h of n, that is less than or equal to m. And again, this part right here is the stuff in blue is all related. This line right here is what implies this condition up here. In order to actually calculate our mh sub n value, we can set 2 to the n to be equal to m, or I guess we'll do the less than or equal to n, 2 to the n, less than or equal to m. Yes, that's the right direction here, less than or equal to m. M on the right-hand side, this 2 to the n coming from over here. And taking the log of this, we'll get that n is less than or equal to the log base 2 of m. And so our VC dimension, dVC, is going to be bounded by the log base 2 of m. And so we've proven a stronger thing actually than what this problem is asking for. It's only asking for, do we know that it's finite? And in this case, we know that it's finite because we've given a concrete finite upper bound for the VC dimension right here. One important thing, or one useful thing to sort of check our work at this point is to think, okay, if we were to plug this number in, plug this formula in right here for our VC dimension bound, how does that compare to our bound on the finite hypothesis class generalization theorem? And so sort of checking the work here, our VC dimension bound on our generalization error En minus E out based on VC dimension is O of the square root of the VC dimension dVC divided by N. I'll leave out the extra terms like that using the O tilde here, the dVC over N. And this is the VC dimension bound. If we were to plug in this log base 2 of m right here for our dVC right here, then that gives us the exact bound that we had for the finite hypothesis class generalization theorem, where that is O of square root log m over n. So the VC analysis, you can, in some sense, totally forget everything that we've done about finite hypothesis classes, and just remember this fact right here about the VC dimension and the VC analysis stuff, and that gives you all the power of everything we did about the finite hypothesis classes. Let's see. Yeah, I realize I'm going fast through here. I just want to make sure that cover one last problem here related to number 7 and important. And that's sort of going in the opposite direction here, that if we have the VC dimension of every infinite hypothesis class, is that infinite? This is going to be false. And there's sort of like a big picture idea about why this is false, and then a concrete counterexample. The big picture idea is that the only reason we started talking about VC dimension was because we needed to provide some sort of bounds on infinite hypothesis classes. And so if every VC dimension if every hypothesis class with that was infinite had an infinite VC dimension, we would not have any bounds over here on our generalization error for infinite hypothesis classes. So that's an intuitive way why I should know that this is going to be false, because we wouldn't have talked about it if it was true. The actual concrete counterexample here, the way that you would explain this is to provide the counterexample. And here we have the perceptron. H perceptron is infinite hypothesis class. But the DVC is finite. DVC equals d plus 1 or theta of d, either of those sufficient for showing the counterexample here. And so providing one hypothesis class that is infinite with a finite finite VC dimension shows that this is false. We will see later on some hypothesis classes that have infinite VC dimension and are infinite, but we haven't seen any at this point. As you're thinking about counterexamples for these sorts of problems, the perceptron is really the only example that we've seen so far about infinite hypothesis classes. But these problem 1 hypothesis classes up here, these are all also infinite hypothesis classes. And so these could potentially work for any counterexamples for the problems down below. And it's not the case that the perceptron is necessarily the only counterexample that you should be thinking of. Okay. Now again, come up for errors. Anybody have any questions at this point? Yeah, Jay.
Could you say one more time? I was kind of writing this down, but the intuition behind why theta is false is that we would not have any bound.
So for questions about problem number 8 here, I said 2 different ways to think about it being false. The second way that I actually wrote down here is the actual proof that it's false. But it's also, anytime you're thinking about these statements up here, anytime you're really thinking about anything in advanced mathematics, it's worth thinking about a sort of meta level about what's going on about the math. And a lot of people spent a lot of time on this math, and they wouldn't have done it if the results were trivial. And here in this case, the question about the VC dimension of every infinite hypothesis class is infinite. If this were the case, then that would mean that our generalization error would always be infinite. Our bound would always be infinite for any hypothesis class like the perceptron. But the only reason we talked about all of this was because we needed some way of making this bound finite. And so the VC dimension over here having finite VC dimension for infinite hypothesis classes, this is our new way of measuring the size of hypothesis classes, coming up with some finite size of an infinite set. And so that's a meta sort of reason about a question like this. Can help you, if you think about the meta sort of questions, maybe for some of these things, why would I have even asked some of the things that we've done in class? Why would we have done it if this was true or false? That can help give you some direction about, should you be looking for a proof or should you be looking for a counterexample? Yeah, real quick.
For purpose of midterms, is it sufficient for us to just explain the rationale, the intuition, or should we? So
for the purpose of the midterms, that meta sort of level is not points for the midterms. That meta sort of level is guide you towards getting the thing that is the mathematically correct thing to say. Good question. We'll end class here a whole 90 seconds early. Start your fall break super early here. And yeah, again, we won't see you on Monday. Hope you all enjoy your fall break. I will have office hours on Friday if you would like to chat about anything.